All right, we're at video F in our 4.6 series, Related Rates, and we are doing a cone problem. And the problem states that an ice cream cone is 7 inches tall and has a radius of 1.5 inches. The ice cream has melted and is dripping out at a constant rate of 0.5 cubic inch per minute. When the ice cream is 2 inches from the bottom of the cone, how is the height changing? So step one, as always, what are we given? What rates are we trying to find? And I think we are certainly told that the rate of 0.5 cubic inch per minute is a volume. And this is going to be a negative. And the reason we know it's negative is that the volume's decreasing, isn't it? So once we have that, what are we trying to find? I'm trying to find how the height is changing. We'll call that dh dt. And that's what we don't know, but we want to know this at a very specific time when h is equal to 2 inches. Okay, so that's what we're given. This is what that's the rate that we have. And so now let's make our picture. And we can certainly say that the total height of this cone is 7 inches. And that the radius here is 1.5. And that's good because the volume of a cone is 1/3 pi r squared h. And I think we have what we need here, but what we have to think about as well is that at one point or another, we're going to have the ice cream at some additional level. And I'm going to call this level h. And we'll say that we have this value r. And as much as I love that h is the distance from the bottom of the cone to where the ice cream level is and r is there, I have these variables and I don't think I want both of them. And there's a way to solve this, and I'm just going to kind of draw a flattened version of our cone to see if you can figure out what it is. There's 1.5. Here's 7. Here's r. And then this length is h. And you guessed it, this is a similar problem or a similar triangle problem waiting for us. So we have 1.5. The big radius is to r. As 7 is to h. And you know what I might do here is I might just reciprocate this damn thing. R over 1.5 is equal to h over 7. And I'm just going to leave it like this because now what we're going to do is we're going to make a formula. And our formula has to involve v and it has to involve h. So, but right now the volume of our cone is equal to 1/3 pi r squared h. So what are we going to do? I don't really want to think about dr dt or think about what the radius has to be. So I think we're better off solving this relationship for r and then substituting in. So our volume formula will be equal to 1/3 1.5 h over 7 squared times h. And what we should probably do here is do a little bit of housework just to make this thing happen. I'm not going to clean it very much. I'll just say that v is equal to 1.5 squared over 3 times 7 squared times h cubed. So what's it time for? It's derivative time. And we can take the derivative of v, and that's very straightforward, dv dt. The volume is changing. It's a function of time. This constant is going to be right there, 1.5 squared over 3 times 7 squared. And now the derivative of h cubed, keeping in mind that h is a function of time, and we do have an application of the chain rule here. And so we'll have 3h squared times dh dt. I typically do like to solve for dh dt before I plug things in. But, you know, today I'm actually going to mix it up. I am going to plug in h equals 2, and then I'm going to solve for it. So dv dt is equal to, oh, and in fact, I'm just going to put that in too. We have negative a half is equal to 1.5 squared over 3 times 7 squared times 3. And I guess we could say that those 3's murder one another. And h is 2, so we can have a 2 squared times dh dt. So I'm not going to make this thing any more beautiful than I need to, but we'll have negative 0.5 times 7 squared over 1.5 squared times 2 squared is equal to dh dt. And I can get us a number here in a second. So we got dh dt is equal to negative 2.72, and the units of this should be inches per minute. So it looks like in 1 minute, all of our ice cream will be gone because we were only 2 inches off the bottom when this thing went down. So I think, once again, this thing feels good in that the height is decreasing, and it seems like because the volume is decreasing, here the height should be decreasing, but it would be decreasing slower, and as the height gets smaller and smaller and smaller, it should decrease faster and faster and faster because the cone, there's more volume at the upper end than there is on the bottom. So yes, I like it.